everybody. In this video, we're going to be talking about vectors and how to add and subtract them. But before we do that, I want to talk for a moment about why this is important. Some things in physics can be described using only a number. The example that we've been doing up to this point is energy. Kinetic energy is just a number. For example, 30 joules. But not all things in physics are just numbers. For example, if I told you that I was in my car traveling at 25 miles per hour, would that be enough information for you to determine where I was going? The answer is, of course, no. I could be going 25 miles per hour in any direction. I could be traveling to San Jose or Salt Lake City or Seattle or any other place on planet Earth that I could presumably reach by car. In order to know where I was going, you would not only need to know the speed at which I was traveling, but the direction I was traveling as well. Many things in physics are like this. We can't just write down a number and call it good. This is why we use vectors. Vectors have both direction and magnitude. So, for example, I could represent the speed and direction that my car was traveling by an arrow. The faster I'm traveling, the longer the arrow is. And the direction that the arrow points tells you what direction I'm traveling. In many cases, it's going to be useful to be able to add or subtract these vectors. We know how to add and subtract numbers. For example, if we have 25 joules of kinetic energy and 10 joules of potential energy, the total energy is just 35 joules. But vectors don't add up quite this simply, and so we're going to take a few minutes to talk about how we add them up. Let's start with vector addition. Suppose we have these two vectors here. We're interested in what happens when we add them together. There are two ways that we're going to see how to do it. The first is by using the graphical representation of the vectors. A vector has two ends. We call them the tip and the tail. The way that you can add vectors graphically is just by taking the tip of one vector and connecting it to the tail of the second vector. Doing that with these two vectors looks like this. To figure out what the final vector is, we just connect the tail of the first vector to the tip of the second vector. This vector here is what we get when we add vector 1 and vector 2 together. As with numbers, it does not matter what order we add vectors in. Vector 1 plus vector 2 is just the same as vector 2 plus vector 1. Another thing to note is that we can always move vectors around as we like. The fact that we took these individual vectors and moved them over here doesn't change them. They're still the same vector. Just as with numbers, we can write this out as an equation. It's just vector 1 plus vector 2 is equal to vector final. These little hats on top of the v's just indicate that they represent vectors instead of numbers. We can move around terms in these equations just like we would in any other equation. Let's use that to figure out how we can subtract vectors graphically. Let's subtract vector 1 from both sides of this equation. This just says that vector 2 is equal to the final vector minus vector 1. When we added vectors, we took one vector and then connected the tail of the second vector to the tip of the first vector. Let's see what this diagram shows for subtraction. Here we're subtracting v1 from v final. Looking at this diagram, I see that v1 and v final are connected at their tails, and v2 is being drawn from the tip of v1 to the tip of v final. This is how we subtract vectors graphically. We place their tails in the same place, and then draw a vector from the tip of the vector we're subtracting to the tip of the vector that we're subtracting from. Let's do one more example to make sure this is clear. Here is two new vectors. Let's try to figure out what v1 minus V2 is. The first step in this process is to just draw these vectors tail to tail. That looks like this. To find the resultant vector, we now just draw a vector from the tip of the vector we're subtracting to the tip of the vector we're subtracting from. In this case, that looks like this. So this long vector here is equal to v1 minus v2. There's another way we could do this. In numbers, subtraction can be thought of as adding a negative number. It's the same with vectors. Subtraction can be thought of as the addition of the negative of a vector. So how do we find the negative of v2? Well, it turns out that the negative of a vector is just the exact same vector except pointing the exact opposite way. So if this is v2, the negative v2 just looks like this. Now we can just add these vectors tip to tail, as we've done previously. And there we go. We got the same answer. The resultant vector is this long vector pointing up and to the left. Well, this method may be nice from a visual standpoint. It's not very mathematically precise. It turns out that there's another way that we can represent vectors that allows us to be a little bit more mathematically rigorous. It's called component form. Let's see what component form is. Consider this vector. We can always draw a vector like this as the sum of two vectors that are perpendicular to each other. For this vector, that looks like this. We typically would call this part the x piece of the vector and this part the y piece of the vector. Notice that this is a perfectly good way of representing that vector. If you have these two vectors, you could always add them up in order to find the vector that you're actually interested in. We can also write this down mathematically. Let's suppose that the length of this vector is 5 and the length of this vector is 3. This diagonal vector then could be written down like this. This notation just indicates that the x piece of the vector has length 5, and the y piece of the vector has length 3. Now let's throw in a second vector and see how we can use component form in order to add and subtract vectors. So we have vector 1 in component form, and this vector 2 in component form as well. Before we add them up, I want to make a comment about vector 2. As with numbers, the components of vectors can be negative. By convention, to the right is positive and to the left is negative for the x direction, and for the y direction, up is positive and down is negative. So let's say we wanted to add vector 1 and vector 2. To do this, all we have to do is add the individual components of the vector. So to find the x component of this vector, we just add up the x components of v1 and v2. So 5 plus negative 1 is 4, and 3 plus 3 is 6. We can now draw what this vector looks like. A vector with x component 4 and y component of 6 looks roughly like this. This is our resultant vector when we add these two vectors. Subtraction works the same way. You just subtract the components instead of adding them. So v1 minus v2 would have this form. 5 minus negative 1 is 6, and 3 minus 3 is 0. In DL today, you worked with a nice app that allowed you to draw a bunch of vectors and see how they relate to each other. I'll post the link to that app in the description of this video. I recommend trying some things out to build your intuition for how this works.